Hello, welcome to another module in this massive open online course. So far we are looking at the Fourier analysis of discrete time signals, particularly periodic discrete time signals, and we have looked at the Fourier series representation of such signals. In this module we will start looking at the Fourier analysis for discrete time aperiodic signals through the discrete time Fourier transform. So we will start talking about, or we will discuss the discrete time Fourier transform and its various properties. Okay. So, we want to start looking at the discrete time Fourier or basically what is also abbreviated as the DTFT, the discrete time Fourier transform, and as I already said, this is basically used for the Fourier analysis of discrete time aperiodic signals. The Fourier analysis of discrete time discrete time aperiodic signals. Okay. And so we consider a discrete time sequence xn consider a discrete time aperiodic sequence all right, and the DTFT of this is given as the discrete time Fourier transform of xn is given as, it is defined as x of omega equals summation n equals minus infinity to infinity xn e raised to minus j omega n. This is the expression for the DTFT, the discrete time Fourier transform. Okay, so this is the expression for the DTFT. Okay. And further one can derive the inverse DTFT as follows. To find the inverse DTFT, we start with integral over pi, let us say minus pi to 2 pi of x of omega e raised to j omega k d omega. I can simplify this as integral minus pi to pi, substitute the expression of x of omega, that is n equals minus infinity to infinity xn e raised to minus j omega n d omega e raised to minus j omega n into e raised to j omega k d omega. Now interchanging the integral and the summation as usual, we have bringing the summation outside, this will be summation k n equals minus infinity to infinity and xn will also come outside since it depends only on n, integral minus pi to pi e raised to j omega k minus n d omega. And now you can see this is a complex exponential, this e raised to j omega n, this is a complex exponential. And the e raised to j omega, the fundamental period is period equals 2 pi of e raised to j omega. So, e raised to j omega k minus n is basically a harmonic, correct, harmonic, there is a multiple of the fundamental frequency which is 1 radian per second. So, if we integrate it over any fundamental period, that is over minus pi to pi, the integral is going to, that is you take any harmonic of omega, integrate it over minus pi to pi, correct, its integral is going to be 0 except when k is equal to n, in which case e raised to j omega k minus n is 1 when k equals n. So, this is equal to, so if, so in this case, so this integral, this is equal to 0 if k is not equal to n, if k is not equal to, and this is equal to basically 2 pi if k is equal to n. So, therefore, this only survives, the integral only survives where k equal to n, and for that it is 2 pi. So, what you get is 2 pi x k. So, we have basically to extract this element x k, we have 2 pi x k equals integral minus pi over pi x of omega e raised to j omega k d omega, which implies that x of k, that is the inverse Fourier transform, inverse discrete Fourier transform, is given as 1 over 2 pi minus pi to pi x of omega e raised to j omega k d omega. This is basically the expression for the inverse discrete Fourier transform. Okay. This is the expression for the inverse discrete Fourier transform. All right. So, this basically gives us the expression for both the discrete time Fourier transform as well as the inverse discrete time Fourier transform. All right. And this is for a discrete time aperiodic sequence x. Okay. Let us look at some of the properties of this DTFT. Let us first start with the spectrum. Now, the spectrum x omega in general, you can see that it is complex. The spectrum x omega is complex, and I can represent x of omega as magnitude x of omega into e raised to j phi of omega. This quantity magnitude x of omega this is the magnitude spectrum. This gives us the magnitude spectrum, and the quantity phi of omega, this is the phase spectrum. So, we have the magnitude spectrum, we have the phase spectrum. Now, further, if xn is real, if the sequence xn is real. Now this implies when xn is real, we have x of omega equals x conjugate of minus omega, similar to what we have seen for the Fourier transform also. X of omega is x conjugate of minus omega. This further implies that basically your magnitude of x of omega is magnitude x of minus omega, because they are conjugate of each other. So basically this means that the magnitude spectrum for real signals, magnitude spectrum equals is even. Further, if you look at the phase spectrum now you can see that the phase of omega, because they are conjugate, phase of omega is minus of phase of minus omega. So the phase spectrum is odd, the phase spectrum exhibits odd symmetry. This is for a real signal. Okay. So, for a real signal, as usual, we have the magnitude spectrum of the DTFT that exhibits even symmetry, and the phase spectrum of the DTFT that exhibits odd symmetry. Okay. And further, a brief note about the convergence. It is also interesting to look at the convergence. Now, the condition for convergence of x of omega converges if, that is a sufficient condition, summation n equal to minus infinity to minus infinity, xn is less than infinity, that is the sequence is, signal is, that is this is a finite quantity. Implies the sequence is absolutely summable, that is if you take the magnitude of each element, sum from n equal to minus infinity to infinity, that is a finite quantity, which means sequence or signal is absolutely summable. The signal is absolutely summable. So, the absolute sum of the signal exists, that is the sum of the magnitudes of all terms from minus infinity to infinity, then the DTFT is guaranteed to exist. Okay, all right. Let us look at the relationship between the Fourier transform and the Z transform, and of course one other thing that you can realize. Okay, that is fine. So, let us look at the relation between the Fourier transform and the Z transform, or the DTFT, relation between the DTFT and Z transform. Now, you can see that the Fourier DTFT is given as summation n equals minus infinity to infinity x of n e raised to minus j omega n, and the Z transform x of z equals n equals minus infinity to infinity x of n z raised to minus n, which implies you can see that if I substitute z equals e raised to minus j omega in the z transform, that is substitute not e raised to minus j omega. In fact, if I substitute z equals e raised to j omega, correct, if I substitute z equals e raised to j omega, then the z transform becomes the Fourier transform. But remember, for the z transform to converge, z equal to e raised to j omega has to be in the ROC of the z transform. Only then can I substitute z equal to e raised to j omega in the z transform to derive the DTFT. Okay, so that's an important, it's an interesting observation, but so very important to realize that it exists only if e raised to j omega is in the ROC, that is the region of convergence of the z transform. So the z transform evaluated at z equal to e raised to j omega, that gives the DTFT. However, this is basically your z transform however, this is only true only possible if z raised to j omega in ROC of xz implies ROC contains the, implies that basically your ROC has to contain the, implies ROC contains the unit circle. So if the ROC contains the unit circle, if the ROC contains the unit circle, then and only then can the DTFT be obtained from the Z transform by the substitution of, by replacing or by substituting Z equal to e raised to j omega. Okay. And you can see that the ROC contains the unit circle if the sequence is absolutely summable. For instance, if you look at summation n equal to minus infinity to infinity xn e raised to j omega n, the magnitude of this is less than or equal to, magnitude of sum is less than or equal to sum of magnitude e xn magnitude e raised to minus j omega n, but magnitude e raised to minus j omega n, this is 1, this is summation n equals minus infinity to infinity magnitude of, which is less than infinity if sequence is absolutely summable, if signal is if the signal is absolutely summable, then this is less than infinity implies ROC implies the ROC contains the unit circle, if because for every e raised to j omega, that is for every z equal to e raised to j omega, this sum, the magnitude of this magnitude sum n equal to minus infinity to infinity xn e raised to minus j omega n, that is the magnitude is finite. So basically the quantity is a finite quantity, all right, okay, and therefore the ROC contains the unit circle, okay, and not generally true, this is not generally true, and therefore this the substitution of z equal to e raised to j omega to yield the DTFT from, to obtain the DTFT from the Z transform does not generally hold true unless your sequence xn does not generally hold true if the sequence xn is not absolutely summable, okay. So this is not generally true if sequence is not, if the sequence is not absolutely summable. Okay. Now let us look at the DTFT of some common signals. So first we start with the impulse, the discrete time impulse. Delta n equals 1 for n equal to 0, 0 for n not equal to 0. This is a very simple function. The Z transform or the DTFT, that is simply n equals minus infinity to infinity delta n e raised to minus j omega n. This is only non-zero only for n equal to 0, at which it is 1, e raised to minus j omega 0, which is 1. So, delta n has DTFT, that is the unit impulse is DTFT, which is unity. Okay. And let us look at the causal exponential signal. Now, when we look at the exponential signal, we consider a decaying exponential, that is A is real first. Let us consider a simple scenario where A is real, and also magnitude of A is less than 1, okay, which means that basically it is decaying as n is increasing, and finally as n tends to infinity, the signal tends to 0 as magnitude A is less than 1. Now, for this we have basically your DTFT is x of omega equals n equals minus infinity to infinity a n e raised to minus j omega n. U n is non-zero only for n greater than equal to 0, and for n greater than equal to 0 it is 1. This simply reduces to n equals 0 to infinity a n e raised to minus j omega n, which is sum n equal to 0 to infinity a e raised to minus j omega n, which is 1 over 1 minus a e raised to minus j omega. So, x of omega you can see is given by this expression 1 over 1 minus a e raised to minus j omega. And further you can see the Z transform of this is also given as a n u n called 1 over 1 minus a Z inverse, and the ROC, remember we already derived the ROC is magnitude Z greater than magnitude A. Now, if magnitude A is greater than 1, or I am sorry, if magnitude A is less than 1, now magnitude of Z greater than magnitude of A implies magnitude of A, that is ROC, is greater than basically the unit circle. What this means is, so we have the magnitude of Z is greater than so ROC includes everything that is magnitude of C. So, magnitude of A is less than 1, correct. So, ROC includes the unit circle, okay, and this can be seen as follows. This implies ROC includes this can be seen as follows. For instance, you have your this thing and you have your circle. So, this is your magnitude z equals 1, this is magnitude z equals magnitude of A less than 1. So, your ROC is basically magnitude of z greater than magnitude of A, which is basically everything outside the circle, which is everything outside the circle, which means everything outside its circle, and you can see it includes the this includes the, so it is everything outside the circle. So, you can see this includes the unit circle. So, if magnitude A is less than 1, correct, then the ROC of A raised to n u n, the ROC of that signal basically includes the unit circle, and therefore, now if you replace the Z transform, that is if I look at the Z transform 1 minus A, and if I replace Z by e raised to j omega, I obtain 1 minus A raised to j omega 1 over 1 minus A e raised to minus j omega, which is DTFT. So, since ROC, so this is possible since ROC contains a unit circle. Now, on the other hand, if you look at the unit step signal, correct, consider the now if you consider the unit step signal u n equals 1 n greater than or equal to 0 and n equal to 0 otherwise. Now, this sequence you can see is not absolutely summable, n equals minus infinity to infinity magnitude u n equals summation n equals 0 to infinity of 1, which is not a finite quantity. This is not a finite quantity. Implies you cannot, so this is of the form a raised to n u n where a equal to 1, okay, with a equals 1. So, magnitude of a is not less than 1, but rather magnitude of a equals 1, which means the ROC does not contain. So, ROC is magnitude of z greater than magnitude of a, right. So, the ROC does not contain the unit circle in this case. So, for if I look at x n x z equals with a equal to 1, x z will becomes 1 minus z or 1 minus z inverse, and the ROC of this magnitude of z greater than 1 does not, which does not include unit circle. Hence, you cannot obtain the DTFT by simple substitution of z equal to e raised to j omega. Hence, if you take that is 1 over 1 minus e raised to minus j omega, that is not equal to x omega. So, DTFT cannot be obtained by substitution for the unit step signal, cannot be obtained by simple substitution of z equal to e raised to j omega in the z transform, because the ROC does not contain the unit circle. In fact, you can show that x of omega for the unit step signal is given as something that is slightly different, that is pi of delta omega plus 1 over 1 minus e raised to minus j omega. This is the DTFT discrete time unit step signal. Okay. So, this is the DTFT of the discrete time unit step signal, that is it contains this additional term. You can see this is pi times delta of omega, there is an impulse at omega equals 0 plus 1 over 1 minus e raised to minus j omega. Alright, so in this module we have looked at several aspects. We have looked at the definition of the DTFT, the inverse DTFT, and also the convergence issues related to the DTFT and the DTFT of some of the commonly occurring or frequently occurring discrete time signals. So, we will stop here and continue in subsequent modules. Thank you very much.